Good evening, sir.
Good evening, ma'am. Am I
Yes, sir,
audible,
we can
ma'am?
start, sir. Yes, you are
Oh,
audible.
okay. Let me start the session now. So, good evening, students. So, in this class, we are going to discuss some numerical problems on moving charges and magnetism. That is, what are all the concepts we have discussed in our previous classes. We are going to discuss the numerical problems related to that. Okay. So, first of all, I will be sharing the whiteboard with you. And after that, we shall discuss the numerical problems one by one. Okay. And here is the first problem. Two toroids. Okay, let me write the question now. Two toroids, 1 and 2. 1 and 2 have total number of turns 200 and 100 respectively. With average radii 40 centimeter and 20 centimeter respectively. Respectively. Full stop. If they carry same current I. I, comma, the ratio of the magnetic fields along the two loops is. This is the question, and let me write the options here. One is to one. Option B, it is 4 is to 1. Option C, it is 2 is to 1. And option D, it is 1 is to 2. So this is the question. We have the two toroids, and they have given us the total number of turns. Okay, total number of turns 200 and 100 in both the toroids respectively, and their average radii also they have given. So if they carry the same current I, the ratio of the magnetic fields along the two loops is. Okay. So now we have to substitute the formula. So what is the formula for calculating the magnetic field within the terms of toroid? So that's the first thing we have to do. We have to write the formula. Here is your solution. Magnetic field within the terms of toroid, that is given by B equal to, that is given by B equal to mu naught Ni by mu naught Ni by 2 pi into R. This is your equation, and for our case we have been given the number of turns in the two toroids and the average radii as well. The current carried in both the toroids is the same. So what we have to do, we have to find out the ratio of the magnetic fields. So that means we have to calculate B1 divided by B2. Okay. So B1 divided by B2 we need to find out. So that means mu naught N1I divided by 2 pi R1. So this will be divided by mu naught N2I divided by 2 pi into R2. Okay. So this implies the next step I will write here. So the next step is B1 by B2 equal to mu naught N1I divided by 2 pi R1. So multiplied by 2 pi R2 divided by mu naught N2 into I. So here what are all the terms that will be cancelled? That is mu naught I will be cancelled, and you will be having N1, okay, N1 by N2 into R2 by R1. So this will be equal to N1 by N2 multiplied by R2 by R1. This will give you the ratio, okay. So now we have to substitute N1, N2 and R2 and R1 values. So here N1 by N2 is nothing but, so let me write that here, B1 by B2 is equal to N1 by N2. N1 means, let me take 200 divided by, N2 is number of turns in second coil 100 multiplied by R2 by R1. So R2 is nothing but 20 centimeter divided by R1 is 40 centimeter. So in that case B1 by B2 will be, so this will be 2 by 1 into 1 by 2. Okay, 2 by 1 into 1 by 2. So what will happen? It will give you 1:1. Okay, 1:1. So 1:1 is the ratio. Okay, 1:1 is the ratio, and it is the final answer. Are you able to understand the solution for this problem? Students, are you able to understand the solution for this problem? Yes, I think it is a very straightforward question. But still, if you have any doubt, you can let me know. So here the correct answer is this thing, 1:1. Okay, 1:1 is the correct answer. Shall we move on to the next problem? Have you all completed this?
Yes, sir.
Okay. In that case, we shall move on to the next problem. Okay. So next problem is a long straight wire. Okay. Or let us proceed with the next problem. Let us do this problem. A long straight wire of radius. So let me write it in the next page. A long straight wire of radius A, okay, carries a steady current capital, a steady current capital I. The current is uniformly distributed. The current is uniformly distributed over its cross section. Full stop. The ratio the ratio of the magnetic fields B and B prime, B and B prime at radial distances A by 2 and 2A respectively from the axis of the wire is from the axis of the wire axis of the wire. is, this is the question, and I am writing the options here. One by two. This is 1 by 2. Option B, this is 1. Option C, it is 4. Option B, it is 1 by 4. Okay, so they have given a long straight wire of radius A carries a steady current I. The current is uniformly distributed over its cross section. So uniformly distributed over its cross section. The ratio of the magnetic fields D and D prime at radial distances A by 2 and 2A respectively from the axis of the wire. Okay. So now we can use Ampere's circuital law to solve this problem. Okay, we can use Ampere's circuital law to solve this problem. How we are going to use that? So that's what we are going to discuss now. So what we should do is we should consider Amperian loops. Okay, Amperian loops of different radius around the wire. Amperian loops of different radius around the wire. So let me draw the diagram here so that you can understand it better. This is the wire. And this is the wire, a long straight wire. So for finding the magnetic field, we should imagine Amperian loops. Okay, Amperian loops. And they have asked us to find out the magnetic fields at different radial distances A by 2 and 2A respectively. So for that, what we should do is we should imagine Amperian loops with radius actually this A by 2 and 2A. Okay. So actually we should imagine the Amperian loops with radius A by 2 and 2A. Okay, and then we have to calculate the magnetic field. Okay. So for the Amperian loop, we should take the Amperian loop like this. This is 1 Amperian loop. Maybe it is in oval shape. Okay. In 3D, it looks like oval shape. So this is the Amperian loop, and this has the radius. This Amperian loop has the radius A by 2. Okay. So this Amperian loop has the radius A by 2. This is one thing. Another Amperian loop we shall consider that will be having a bigger radius, that is 2A. Okay, so 2A. So in 3 dimensions, it also looks like an ellipse shape. So this one is having a larger radius, and the radius of this Amperian loop is actually 2A. Okay. Now we have considered the Amperian loop. So we should proceed with the solution for this problem by using Ampere's circuital law. And now we shall proceed with this thing. So how we can proceed? What is the Ampere's circuital law statement? So the Ampere's circuital law statement is integral B dot dl. Integral B dot dl equal to mu naught into I enclosed. Okay. Integral B dot dl equal to mu naught into I enclosed. So this dl here is the Amperian loop circumference. Okay, amperian loop circumference. So that should be equal to mu naught into I enclosed. So I enclosed means how can we find out the I enclosed? We have to find out the current per unit area. Okay, because it is uniformly distributed over its cross section. So we have to find out the current per unit area and then multiply the area of the loop. Okay, multiply that by the area of the loop. In that way, we should calculate the current enclosed. So for the smaller loop, first of all, let me proceed. So for the smaller loop, that is in rose color here. So smaller loop B into this dl. Dl means that is the circumference of this loop. For the smaller loop of radius a by 2, what we should do? B into 2 pi into a by 2. This should be equal to mu naught into I enclosed. I enclosed means I divided by pi a square. That is current per unit area multiplied by the area of the loop. Okay, current per unit area multiplied by the area of the loop. So current per unit area is, so overall we are having that radius as a. So current per unit area is pi divided by a square. So pi divided by I divided by pi a square. So I divided by pi a square into pi into a by 2 the whole square. So here you can take b into pi into a. Okay, b into pi into a. This is equal to mu naught into I. So this pi a squared and this pi a squared will be cancelled and divided by 4 it will be remaining, divided by 4. Okay, so b into pi a equal to mu naught into I by 4. So what is the magnetic field now? So b equal to mu naught I divided by 4 pi into a. This is the magnetic field, and of course this is the magnetic field due to the smaller loop of radius a by 2 from the axis of the wire. So at a distance a by 2 you will be having this much of magnetic field. And now the magnetic field for the bigger loop we have to do. So the magnetic field for the bigger loop we have to do. So for the bigger loop, so it is outside the, actually the point is now outside because at a radial distance 2a you have to find out. Okay, so initially the straight wire is having a radius a and the magnetic field b which we have calculated here for the smaller loop is at a point a by 2. That is the point which lies inside the wire. That is radius a by 2 means it actually lies inside the wire, so that is a by 2. So now the bigger loop means the radial distance is 2a. So that means it is outside. So the bigger loop b prime, okay, b prime into 2 pi into 2a. Okay, this is equal to mu naught into total current, mu naught into the total current I. Okay, mu naught into total current I. Why there is a difference? Here we have straight away substituted I, but here we have used I by pi a squared into pi a by 2 the whole square. Why we are doing like that? Because the straight wire is having the radius a, and the magnetic field B is at radial distance a by 2. Okay, a by 2, which is a smaller distance than this radius. That means the magnetic field is uniformly distributed inside the loop. So that's why we have found out current per unit area multiplied by the area of the Amperian loop. But here for B prime, the radial distance is 2a. So that means it is much greater than the radius of the wire. That means it is lying outside. So the total current, okay, the total current enclosed is mu naught into I as such. Okay, mu naught into I as such. So B prime into 2 pi into 2a equal to mu naught I. So B prime. So B prime So B prime here is actually mu naught I by 4 pi into A. From this equation, B prime into 4 pi A equal to mu naught I. So and then B prime is equal to mu naught I by 4 pi A. So now what is the ratio of the magnetic field? Here you see for B also it is mu naught I by 4 pi A, and B prime also it is mu naught I by 4 pi A. Then what is the ratio? It should be 1. Okay, 1:1 or 1. So the correct answer is option B. Okay, so B by B prime. So it is B by B prime or B prime by B, whatever way you can take. It is mu naught I by 4 pi A divided by mu naught I by 4 pi A. It should be 1:1. So the correct answer is actually option B, that is 1. Okay. Do you all understand the solution for this problem? Students, any doubt in this problem?
No doubt.
Okay. So in that case, we shall proceed with our next problem. So the next problem is two identical long conducting wires. So let me write it in the next page. Two identical long conducting wires. AOB and COD. AOB and COD are placed at right angles to each other. right angles to each other, such that one is above the other. One is above the other. And O is their common point. And O is their common point. The wires carry I1 and I2 currents. I1 and I2 currents respectively. Full stop. Point P is lying at a distance d. Is lying at a distance d. From O. From O. Along a direction. Along a perpendicular. Along a direction perpendicular to the plane containing the wires. Containing the wires. Full stop. The magnetic field at the point P will be the magnetic field at the point will be this is the question. Now I am writing the options here. Mu naught by 2 pi d into I1 by I2. Option B. Option B. Mu naught by 2 pi d I1 plus I2. And option C. Option C is mu naught by 2 pi d I1 squared minus I2 squared. Option B is mu naught by 2 pi d into I1 square plus I2 square whole power 1 by 2. So this is your question. Two identical long conducting wires AOB and COD are placed at right angles to each other such that one is above the other and O is their common point. The wires carry I1 and I2 currents respectively. Point P is lying at a distance D from O along a direction perpendicular to the plane containing the wires. The magnetic field at the point P will be. This is our question. So how we are going to proceed with this thing? So first of all, we need to make the diagram and then we should proceed. So let me do the diagram in the next page. So first of all, let me draw the wire AOB. This is the wire AOB, okay? A, O and B, okay? A, O and B. And we have one more wire COD that is perpendicular to this thing. So for that, let me use another color. So here you have COD, okay? This is C, and this is D. They both carry currents I1 and I2 respectively. So that means here we have I1 and here we have I2. And you have a point P lying at a distance D from O. Okay, point P is lying at a distance D from O along a direction perpendicular to the plane containing the wires. So it means if you consider the CD as x-axis and AB as y-axis, then point P is lying at a distance perpendicular to the plane means it is lying on z-axis. Okay, it is lying on z-axis. So that will be like this. Somewhere here along the z-axis, the point P is lying. Okay, the point P is lying here at a distance D from O. So this distance is D. This distance is D. So we have made the diagram. Now we should proceed with the solution. So according to the point P, okay, according to the point P, you have the magnetic fields produced by wire AOB and COD, and that magnetic fields will be right angles to each other at the point P. Okay, at the point P, you have two magnetic fields. Magnetic field due to this wire AOB, okay, and the magnetic field due to the wire COD. So both these magnetic fields are at right angles to each other. So the net field is given by, so for that also I will be making the diagram here. So this is, if you consider this B1 and this is B2 at the point P, okay. So at the point P, you are having magnetic field B2 produced by wire COD and magnetic field B1 produced by wire AOB. So this is point P and the net field is along this direction. Okay, the net field is along this direction. The net field is represented as B net. Okay, B net. Okay. So the B net is now given by B net is now given by, since both are vectors, B1 squared plus B2 squared square root of B1 squared plus B2 squared. Okay, square root of B1 squared plus B2 squared. So B1 for a straight wire, okay, for a straight wire. B1 means the field due to AOB. So that B1 is given by B1 equal to mu naught I1 by 2 pi into D. Okay, this is B1. And B2 is equal to mu naught I2 divided by 2 pi into D. So you have to take the square root and then you have to go for the addition. So B1 squared, that is mu naught squared I1 squared by 4 pi squared D squared plus mu naught squared I2 squared divided by 4 pi squared D squared, and square root you have to apply. So when you take all the terms common, you can take mu naught by 2 pi D as common. So in that case, within the bracket, you will be having root of I1 squared plus I2 squared. So that means it is mu naught by 2 pi D into I1 squared plus I2 squared whole power 1 by 2. So that is option B. Okay, that is option D. This is how you need to solve this problem. Okay, can you understand this? Students, can you understand the solution for this problem? Anyone have any doubt?
No, sir, no doubt.
Okay. So now we shall move on to our next problem. We shall move on to our next problem. So I will write the question here. When a proton, okay, when a proton is released from rest in a room, when a proton is released from rest in a room, it starts with an initial acceleration A naught towards west, towards west, full stop. When it is projected towards north, when it is projected towards north with a speed v naught, with a speed v naught, it moves with an initial acceleration. It moves with an initial acceleration v a naught towards west, towards west. Full stop. The electric and magnetic fields. The electric and magnetic fields in the room are, in the room are. So this is the question. I will be writing the solutions here. M A naught by E west, comma 2 M A naught by E V naught up. Option B is M A naught by E west 2 M A naught by E V naught down. Then option C, M A naught by E east, comma 3 M A naught by E V naught up. So M A naught by E east, comma 3 M A naught divided by E V naught down. Okay, so this is the question. So when you observe the question carefully, you can get some hint to simplify your procedure of solving the problem, because here a proton is released from rest in a room and it starts with an initial acceleration a naught towards west. Okay, so when a proton is released initially from rest in a room, the proton is at rest initially and it is moving with acceleration a naught towards west. Okay, When it is projected towards north with a speed v naught, it moves with an initial acceleration 3 a naught towards west. In the first case, the proton is initially at rest and it is just released so that it starts with an acceleration a naught towards west. But in the second case, you are actually projecting the proton towards north with a speed v naught. In that case, it moves with, okay, in that case, it moves with an initial acceleration 3 a naught towards west. The electric and magnetic fields in the room are. So on seeing the question and the solutions, okay, you can actually eliminate two of the incorrect options from the question straight away. So how can you do that? Can anyone tell me? You can actually eliminate two of the incorrect options straight away, so that you will be left only with two options to choose from. So from that two options, one option is the right answer. But what is the logic, or based on which concept you can rule out the two incorrect options? Can anyone tell me? On seeing the question, what is the hint? Yes, any hint, students? Anyone? You can make it. You can make a try actually, no issues. Okay, let me tell you. So actually, initially the proton is released from rest, but still it moves with an acceleration a naught towards west. Okay. So whenever a proton released from rest gets an acceleration a naught towards west, so how did it get its acceleration? That means it has some electric field, okay? Because the force acting on a charged particle in an electric field is F equal to Q into E. And when you have the vector notation, when the charge is a positively charged particle, then your electric field and the force are in the same direction. Okay, when the charged particle is a positively charged particle, then the force experienced by the charged particle is in the same direction as the electric field. When the force is in the same direction as electric field, then the acceleration of that particle is also in the same direction. That is A equal to F by M. Here the proton is moving towards west. Proton is a positively charged particle. Since it is moving towards west, there should be an electric field in the west direction only. Okay, because it is a positively charged particle. So the force acting on the proton should also be in the same direction as electric field. When the force is in the same direction as electric field, the acceleration should also be in the same direction as the electric field. So the acceleration should be in the same direction as electric field. So acceleration is towards west. That means in the question initially they have asked you electric field. Okay. So electric field means the first part of this answer should be the direction of electric field. So here you have west in options A and B. That means between these two options, one is the correct option. So the electric field cannot be in the other direction. Okay. The electric field cannot be along the eastern direction. So these two options are ruled out. Since proton is a positively charged particle, F equal to Q into E. Okay, F equal to Q into E. So force and electric field should be in the same direction. So acceleration and electric field should also be in the same direction. So initial acceleration is towards west. That means the electric field should also be towards the west direction. So these two options, among these two options, you should choose one. These two options are ruled out. Okay. So now you have to choose which one is the right option among between these options A and B. Okay. So for that, what you should do? So it is actually the force acting on a charged particle. Okay, force acting on the charged particle. So the acceleration 3 a naught towards west. How do you get this? When you have magnetic field simultaneously, you will be getting this 3 a naught towards west. Okay, you will be getting 3 a naught towards west. That means your force should be, let me write in the other slide. That means the force should be Q into E plus B cross B. Okay, so that means F equal to QE plus QVB. Okay, so the acceleration should be equal to force by mass. And here, what is the mass of that proton? Have they given? They have not given. So let us consider that it is m. Okay. So here the acceleration is given by q into e. Okay, q is nothing but the charge of the proton, right? So let us consider that it is e. Okay, e q into e. So e into electric field. Electric field is e. I am writing it based on this equation. Okay, e into e plus e into initial velocity is v naught into b divided by m. It should be along the western direction. Okay, so it moves with an initial acceleration 3 a naught towards the west. So 3 a naught is towards the west. Okay, or e v naught into b plus ee equal to 3 a naught into m. Okay, 3 a naught into m. So this e v naught b. So e v naught b equal to 3m a naught minus e into capital E. E into capital E. So initially, in the first scenario, a proton released from rest moves with an acceleration a naught along the west. So m a naught equal to E into electric field. This is the first case. Okay, the first case here, you can see when it is released from rest, it moves with acceleration a naught towards the west. So it is m a naught equal to E into capital E. So that means here what you can do, E into V naught equal to 3m a naught minus, instead of E into capital E, it is m a naught. So E into V naught be equal to 2m into a naught. Okay, 2m into a naught. So the magnetic field B is now given by 2m a naught divided by E V naught. Okay, so this is the value of magnetic field. So it can't be in the upward direction, it should be in the downward direction only. Okay, then only you will get the resultant force. So it is acting in the vertically downward direction. So this is the right answer. That is option B. Okay, option B is the right answer. So I think it's time up for us. So let us keep it this much for this session, and we shall meet again in our next class. Thank you so much for joining the session.
Thank you, sir.
Thank you.